Yeah, good evening, respected faculty members. I am Sudhir, so mentor for this particular FDP program. So, shall we start the session? Welcome to 15-day industrial training program on AI-driven embedded product development, and it's day 6. It's about advanced PCB design considerations. First, we will discuss about high-speed PCB design principles. Like for any high-speed PCB, we need to follow some principles in terms of signal integrity and EMI and EMC. So as a first topic, we will discuss about what are the design principles we should follow for signal integrity and EMI and EMC. And later we will discuss about thermal management and heat dissipation strategies, which is very, very important. For industry grade PCB, most of the PCBs are working in the high temperature conditions, and most of the components will produce the temperature thermal. So there should be a thermal management mechanism, and at the same time, heat dissipation strategy should be there at the time of PCB designing. We will discuss about thermal management and heat dissipation strategies, and later we will discuss about PCB design for manufacturability (DFM) rules. Yesterday we discussed about DFM rules. Today also we will discuss about what are the design constraints for design for manufacturability and cost optimization techniques. And later we will discuss about mechanical aspects for PCB design, like enclosures and mounting holes and connectors, like how mounting holes should be and how the connectors placement on the PCB. We'll discuss about mechanical aspects today, and followed by case study. Like we will go for the optimization of your PCB for industry grade application. Like for any industry grade application, we should take care about high speed PCB design principles for signal integrated and EMI, and we should follow thermal management and heat dissipation, and we should check DFM rules, and there should be a cost should be optimized design. Our design should be like a towards cost optimization, and mechanical aspect should be proven. So that is how any industry grade applications, followed by AI driven reliability and design for manufacturing. We will discuss about how entire process is optimized using AI trend. So this is about today's session. So we will go in detail. Uh, First, we will discuss about what is the signal integrity aspect in a high-speed PCB design principles. Okay, so for any signal integrity, we should maintain. Just give me a second. So simply, we already discussed like there should be a short track. Okay, and the second one is the width of the track based on the component type, whether it is a power related or analog related or digital related, and we should work on minimizing the crosstalk. So using uh, parallel tracks or differential pair, we can minimize the crosstalk possibility, and we should maintain control impedance. So when there is a transmission lines, we should maintain consistency in the impedance to avoid reflections and signal loss. So control impedance is nothing but we should maintain parallel tracks, and we should maintain proper spacing between the tracks, and termination techniques. So in some of the PCBs, there will be a no proper termination. So let us assume one track is from controller to IC, but there is a improper connection. Like there is a incomplete track. Are you getting incomplete path? I can say incomplete path. So there will be issue at the time of PCB execution. So if you are not able to complete the path of one particular track, it will uh, it will uh, it will be generating the signal degradation and mismatch in the impedance. So if we take any track from one component to other component, it should be terminated at any other end at component. If there is no connection is required, we should at least go with a proper bias termination kind of thing. So these are some of the thing we need to follow for signal integrity. Control impedance should be mapped, and we need to focus on crosstalk minimization and proper termination techniques we should follow, and we should focusing on minimizing in reflections. So that already I told, right? If any abrupt changes in traces, or else incomplete unnecessary tracks, unnecessary wires. Thing here is wires should be there for the heat dissipation and the PCB size reduction. If there are wires, we can reduce the PCB size. We can go for multi-layer. If you are going for a unnecessary wires, At the same time, unnecessary tracks, like if you take one track, it should be terminated. So if you are going with the unnecessary tracks, unnecessary wires, it will lead to the signal loss. And one more thing, let me simplify some points for signal integrity. First thing is, there should be a track length as short as possible. Second thing is, there should be a no sharp edges. If you see here, just give me a second. If you see here, the signal is transmitting from here to here, right? If it is like a sharp edge, there will be a chance for signal loss. So we should not go for a sharp edge of the tracks. It should be like a smooth track, smooth curve. And one more thing, if any high signal takes place, for high signal, we should not go for a bias, because for high signal, high speed signals, if you go for a bias, there will be a chance for signal loss. So we should not go for a high speed. We should not go for a bias for high speed signals. So those are the things we need to follow. We will discuss about EMI and EMF. So if we take any component, we should go for a proper grounding. Thing here is, if you are maintaining proper ground plane for high speed signals and high temperature producing components, it will reduce the noise and improve the signal integrity. So if you take let me show our PCB. So is my screen is so if you take this particular PCB, okay, so this is what power related segment. So power, we are using metal component. Where there is a power change, there will be a huge chance for heat generation. Heat generation can be happen in three different techniques. One is, we can go for a metal placement. And the second thing is liquid, like vapor mechanism we can use, and polymer. For heat compensation, we can go for either metal, as I shown. Second thing is polymer, like liquid based heat compensation is there, and metal based heat compensation is there, and polymer heat compensation is there. Polymer is like, if we take this particular IC, if this is a high heat generation kind of thing, let us assume this is not the high heat generation technique, but let us assume this is the high temperature, high heat generation IC. So we can go for a polymer material. So we can stick that particular material on this particular IC so that it will compensate the heat. So heat compensation can be takes in three ways. One is polymer material, and the second one is metal based material, and the third one is liquid based material. Okay, and one more thing, if you see, I guess like this is not up to mark. So if you see, there is a no proper copper pouring, like uniformity proper copper pouring we can't identify. Just give me a second. So if you see this particular PCB, okay, so see this particular phase, okay, see this particular thing. Here is the high copper volume. Here is the high copper volume, and some places is low copper placement. This is high copper placement, this is low copper placement, because whenever there is a main controller which is need to the high switching, so it will generate the high temperatures. So the copper pore width is 2Z. Okay. So basically, let me introduce one more term here. We will call copper thickness in OGs. Sorry, OZ. Copper thickness we will call, we will measure in OZs. So if it is like a high temperature kind of thing, high heat producing kind of thing, then we will go for 2 OZ. Okay. If it is like a low temperature producing, then we will go for a 1 OZ. Okay. So basically, which defines the thickness of that particular copper material on the at that particular place. Okay. So let me come back to the presentation again. So To reduce the EMI, we already discussed proper grounding should be there for signal integrity. If we go for a 2 to 3 layers, one dedicated layer will be maintained for the ground plane and power lane, so that the heat dissipation will be uniformly distributed and eventually it will be reduced. So second thing is shielding techniques. So I already told, right? We can reduce the heat in three different mechanisms. One is shielding. Metal shielding we can use to prevent the particular interference and external sources, and the vapor cooling techniques we can use. Slowly we will go for the further slides. And next one is filtering and decoupling capacitors very near to the power circuits, and differential pair. So in yesterday session we discussed about there should be a differential. We should maintain differential pair with equal length routing, so that eventually it will reduce the common mode noise. Can anyone let me explain about what is common mode noise? So if you take two lines, A minus and A plus, so both will generate the noise. So both are in opposite polarity, so that both the noise will be cancelled and the signal will be passed without any noise. That is what the concept of this particular differential pair. And layer stack up considerations. Already we told, like, we can go for a multi-layer PCBs with well-planned ground and power distribution to control the EMI. Now we see about thermal management and heat dissipation. So thermal management, already told, right? Polymer material we can use, and metal material we can use, and liquid material we can use. So coming to the copper thickness, we will deal in OZs. If it is like a high power dissipation is required, we will go for a 2 OZ. If it is like a normal signal, we will go for a 1 OZ. And we are using GaN material. If we take here GaN material, you see GaN material will be used. So that stands for gallium nitrate. We are using gallium nitrate for heat dissipation purpose. So some heat dissipation techniques are thermal wires. So we should maintain as many as thermal wires under the ICs. So ICs will produce the, like, which are the digital logics which will produce the high temperature. So under the particular IC body, we should maintain multiple thermal wires, so that on the top body we are maintaining signal tracks will be through on the top layer. So in the bottom layer or in the inner layers we are maintaining ground plane or else power plane. So that will be transferred. The high temperature will be passed to the ground plane or else power lane, so that temperature will be compensated. And the second thing is heat sinks. We already said, right? MOSFETs and voltage regulators are dealing with the attached heat sinks. Metal bodies will be used so that heat will be compensated. And copper core and planes. So increase the copper thickness. So basically for normal materials we will go for a 1 OZ. For high thermal producing material we will go for a 2 OZ. Like thickness of the 1 OZ equal to 28 gram of the copper. So we will go for a 2 OZ, like almost like 56 grams of copper. And thermal pairs and conducting material we should use. So using thermal interference materials, TIM. GaN is one of the TIM material. It will compensate the thermal interference. It will avoid the thermal interference with the signal. That gallium nitrate will be helpful for that particular heat dissipation. And component placements. Basically, we already said, right? All the temperature producing elements need to be placed as far as possible. And one more thing, heat dissipation techniques. There are a number of heat dissipation techniques. One is for MOSFETs, we will go for a metal body, and we need to maintain thermal pads and conducting materials and thermal wires and component placements as far as possible. And under the IC, we will go for a thermal wires and thermal pads. So component placements. So these are the some of the heat dissipation techniques. Okay. And there are other techniques as well. One is passive cooling. We will use natural convention method for heat dissipation, like copper pouring and track width, track length. These are the passive cooling techniques. And the active cooling techniques, we will go for a fan. External fan will be deployed there, or else liquid cooling. So basically what will happen is if you take this particular tube, there will be one mechanism, that is vapor chamber condensation. Vapor chamber cooling mechanism is there. So there will be a vapor, and the high heat air will be passed through this particular tube, and then the vapor will be condensed. It will be a in loop process. Continuously that loop will be taking place. The hot air will be passed through this particular pipe. There will be a vapor. That vapor will be converted as a condensing material, and the process will be repeating. So all the industry level PCBs will produce high level PCBs, so that we will place fans, we will place this particular tube. Nowadays, in all the gaming mobiles, this vapor chamber cooling mechanism will be utilized. In all the gaming mobiles, this kind of mechanism will be used for heat dissipation and heat spreading techniques. And we will utilize like thermal wires and heat pipes for distribute heat evenly. So this is about some of the cooling techniques. Now we will about PCB design for manufacturing, DFM, design for manufacturability and cost optimization. So let me say first, like, how can we reduce the cost? So if we take PCB single, like you can give the order like PCB as a complete sheet. So give me a second, let me show our PCB. So if we take this particular PCB, okay, this PCB in a piece individual quantity we can order to the manufacturer, or else we can go for a complete sheet. If we take this particular bare PCB, they will give 6 bare PCBs on a single sheet. 6 PCBs or 100 PCBs or 30 PCBs on a single sheet. So finally the cost of the PCB will comes down. Like how I will explain. So if you go for a PCB panelization, that term is called panelization. If you go for a PCB panelization, then the unwanted part will be lesser. We can reduce the material wastage in a lower manner. Like we can reduce the material wastage, so that the cost of the entire PCBs, all 5 PCBs, all the 10 PCBs will comes down. That is one concept called panelization. And the second thing is component spacing. We should not place all the components as close as possible. We said if the spacing between components is higher, then size of the PCB will increase and the cost will be increased. That is the first class. And the second one is loop area minimization. Loop area will be improved so that EMF effect will take place. So to avoid those two issues, if we are keeping all the components side by side, very close to each other, then heat will be produced. So which is also unwanted. So component placement, there should be a proper spacing, proper clearance. It will be helpful for easy soldering. And at the time of assembly and at the time of soldering, if we are maintaining proper spacing, it will be helpful for heat dissipation, at the same time easy soldering and assembly. And panelization technique will reduce the material wastage and reduce the cost of the PCBs. And vias design, I already said, right, we should not go for a vias. Vias are very helpful if you go for a multi-layer, from one layer to one layer. For signal transmission purpose, we will use vias. And for thermal, we will go for a temperature compensation, we will go for a thermal vias. But if we go for a high number of vias, for high signal will be lost. That is the one thing. Second thing is, if you go for a vias, it will increase the cost. The number of vias, the PCB manufacturing will be takes cost based on the number of vias. So we should not go for unnecessary vias until and unless heat dissipation purpose or else multi-layer purpose. And we should maintain standard space or width. Okay, so these are some of the DFM, like design for manufacturability techniques. And solder mask and silk screen considerations, ensuring clear labeling. For each and every component, we need to maintain clear labeling for like capacitor we are using C1, C2, C3, for resistors R1, R2, R3. Proper labeling we should use, and proper masking coverage should be used to avoid short circuits, to maintain proper debugging and proper understanding of the particular PCB. So these are some of the considerations while we are going for a DFM. If we are going for a panelization, cost will be reduced. And if we reduce the number of wires, cost will be comes down. And if the track width, and if you are maintaining proper spacing, component spacing, which will be helpful for easy soldering, so that soldering time will be decreased. So eventually assembly time, assembly cost will be reduced. So these are the some of the techniques to reduce the cost of the PCB. And later we will cost, how can we reduce the cost? So minimizing the PCB layers. If it is like a less number of components, it's better to go for a single layer. If it is like a high density components, we can go for a 2 layer, 3 layer. So there is a chance for go for n number of layers, but we should minimize the number of layers so that cost of the PCB will comes down until unless it is required. So there should be a trade-off point between number of wires and number of wires and number of layers and number of components. So depends on all those three parameters. We should focusing on trade-off point so that the cost of the PCB will come down. And selecting the standard components, because all the industries are academic institutes will face a difficulty. Like if you are going for a less available components in your design, like we can design to meet the particular requirement, but if the particular component, the particular part number is not, the particular part is not available or less in count at the manufacturer, we should wait for a its reproduction. At the same time, the cost of the components will be higher. So always it's preferable to select widely used components and standardly available components to reduce the cost. And the second one is automation should be there. Our design, our component selection, some components will not fit for automation, like auto assembly. So our component selection should be met with whether that component is suitable for automated assembly or not. So while designing PCB, we should check whether that component is widely available or not. What is its lead time? Lead time stands for if the component completely, if the manufacturer completely done with his production, like whatever the stock is having is sold out. So it will take its lead time to get the new piece. If some X company is there, they are producing some controllers. All the controllers are out of stock, then it will take that particular lead time to get the new piece into the market. So we should select the components such a way that which is having widely available and least lead time. Least lead time based on the that depends on the manufacturer. So and the components what we are selecting, that should be suitable for equipment what we are using for automated assembly. So it will reduce the cost of the particular PCB. And now we see about mechanical aspects for that particular PCB. So simple thing, if we take any enclosure, it should fit in that particular enclosure. The PCB should be inside the particular enclosure, and there should be a space between PCB and the top layer so that there will be a chance for ventilation. If you are tightly fitted, then there will be a heat generation issues. So what are the components placed on the particular PCB will generate the heat. So if you are tightly fit the particular enclosure, so the life period of the components will comes down. So ventilation should be there, and the material what we are using, it should protect our PCB from environmental conditions. So most of the embedded systems are in this field, like in the real time environment. So our mechanical casing should be protect for rain, temperature, and other things, harsh environmental conditions, I can say. So one more thing, mounting instructions and mechanical stability. If you see this particular PCB, there are on the four corners there will be a mounting holes. These mounting holes will be used to fit this particular PCB with mechanical body. So that mounting hole should produce the stability for the particular PCB, and it should be vibration free. If you whatever the material we are using for this particular stabilization, okay, if this particular material is sensitive to the vibration, some of the analog circuitry on the PCB will be affected. If this particular PCB will be vibrated because of this particular mechanical casing, so the analog circuitry will be affected, because analog circuitry are very sensitive because of they are continuous in the nature. So we should select this particular material which will resist the vibrations, and using standard standoff and spaces. So these are some of the things we need to follow for mechanical thing. And one more thing, if you are taking a bunch of wires on the PCB, it should be a strain relief. If it is a tightly fitted, if there is a no free hand or like space on the particular bunch of wires, strain will be improved, and eventually the life period of this particular wires will be damaged. And if it is like a high dissipation components, life period will be decreased. And cable routing and connector placements. All the connectors should be placed at the edge of the PCB, so that most of the connectors are having external connections, so that these can come out of that particular housing. So connectors placement should be very effective, and connectors are meant for external connections. So whatever the wires we are placing on the PCB, it should be a strain relief, or else it will be damaged. So these are some of the precautions we should take care. And now we will see about how can we optimize a PCB for industrial applications. Simply for any industry applications, simply signal integrity is required. So signal integrity we will get it with a like less track length, and proper adequate track width, and proper spacing between the tracks to reduce the EMI effect, and proper wires if you are going for a multi-layer, and proper thermal wires. So these are some of the things, and we should maintain proper ground plane and shielding for EMI effects. To reduce the EMI, we should go for a proper ground plane, shielding, and filtering capacitors are required. And for thermal management, we already said like integrated copper pores, OZ. Already we said like OZs, and thermal wires and heat sink materials to dissipate the heat. And DFM considerations, we already said design for manufacturability, use standard track widths, and minimize the PCB layers, and optimize the component spacing for cost effective thing. And mechanical strength, our this particular holes should be mapped with mechanical equipment, and whatever the connecting material we are using, those are vibrant free. So these are some of the precautions we should go for a industry grade PCB. Now we'll see about how AI will affect these particular designs. In like just 1 year before, we should go for all the things. Like just give me a second. Let me go for a full screen. So now AI will analyze. If we are at the initial time, if we are AI tools are asking about DFM files. DFM files stands for our Gerber file, a design file, a BOM file, and PNP file. If you are providing these particular files and our requirement, the AI system, the software will analyze what is the precautions we should take care for high frequency signals, and where there is a chance for EMI. So if there is any shorter gap between two tracks, then EMI prone will be takes place. It will highlight where will be a EMI effect. And machine learning techniques will use for parallel routing and crosstalk avoidance. If there is any crosstalk chance as a design, it will recommend like there will be a chance for crosstalk. So it's better for go for a orthogonal routing or as a parallel routing. So these kind of recommendations it will give. And automated analysis flags. So for high switching signals, it will recommend whether the number of thermal wires are sufficient or not. If the number of wires are higher in count, it will highlight again. Cost will be increased. So these kind of things will be recommended by AI tools. And for high switching signal, whether we are using a proper shielding or not, proper ground plane we are using or not for isolation. These kind of suggestions we are getting from the AI tools. And again, clock traces are missing. If any signal, any track is abruptly closed without any successful path, it will recommend this particular path is open. So which will transfer it, that particular track is missing. So you should complete the path. You should complete the track. These kind of recommendations will be given by AI. And the system recommended like decoupling capacitor, whether too close placed or too far placed. So what is the estimated distance you need to place? These kind of things will be recommended by AI tools. And one more thing. So when which zone is affected for thermal, whether we are taking actions for thermal reduction or not. So if there is any power related circuits, whether if you are placing proper thermal compensation, it will be in green. that simulator will show in a green color. If it is a highlighted thermal affected, it will go for a red highlighted kind of thing. So we should either go for a copper pouring, or else we should go for a thermal compensating material. These kind of recommendations it will be give for heat compensation techniques, and which is very important, cost. So if you are closely placed components, again it will recommended. If we far away place the component, it will recommended. If unwanted wires are there, it will recommended. And if the mechanical casing is out of the body, then it will suggest this particular mechanical body is not fit this particular PCB. And one more thing, which is very important, in 1 year and a half before, we don't have whether that particular selection component is fit for our PCB or not. Basically, we will give design for manufacturer. Manufacturer send the PCB. After sending this particular PCB, just give me a second. Let me show our PCB again. So after sending this particular PCB, okay. So if we take this particular dip component, some of the dip components if we are maintaining, if you are unable to follow the user data sheet of the particular component, if you are unable to place proper spacing, proper footprint, then when we are receiving the component, the footprint was mismatched. The component is unable to fit in this particular PCB, so entire PCB will be damaged. So while we are giving for DFM files and BOM file, Gerber files, the particular AI tools, the tool will go for a part number and pitching, and whether the selected manufacturing part number will be fit for that particular through-hole component or not, whether properly CAD was provided or not. This kind of information we are getting in the tool itself. So again, it will go for a analyzing the reduced power paths. If you are unwantedly crossing power paths along with the signal tracks, it will recommend power paths should be somewhere else and signal tracks are somewhere else. If we take red lines and green lines, one is signal related pins and the red one is power related lines. Both should not cross each other, even in the multi-layer. So it will recommend that was the hot spot. If it change, and if you see like what are the heat dissipation elements, so that if we are going for a heat minimization, so that the life of the particular PCB will be improved. So recommendations regarding long component life and flags mechanical weak points for reinforcements. If you are if required in middle also, it will recommend one hole for mechanical strength. Depends on the number of components we are using on that particular PCB. And it will validate the diodes, TVS diodes, and power current protection, and ensures the voltage, current, tracks, widths, everything on the A2s nowadays. So this is about how should we take care about DFM rules and how AI affects this particular minimization techniques. Nowadays, engineers work is very easy and like just before 1 year, 1.5 year back. So we need to bring the PCB. We need to check whether heat is generating with heat guns. There is a heat guns. While running on the particular PCB, we will take heat gun and we will check what is the temperature. So if something is high temperature generation, then we will think about copper port should be higher, or else thermal wires we should take care, or else any liquid material, or else metal material, or else vapor material tubes. What mechanism we should go for? We should think about once we receive the PCB, we will think about the particular mechanism. But nowadays, before going for a manufacturing, we simply pass our Gerber file, BOM file, design files, everything to the AI tools. So AI tools will recommend this area will be affected for heat. This area is weaker for mechanical housings. These kind of recommendations are we are getting from this particular AI tools. So again, BOM, when we are placing BOM nothing but bill of materials. What are the components we are using on the PCB that we called as a BOM. So while we are passing that BOM into the file, it will go for the all the manufacturers, all the vendors, whether the component is available or not. If not, you should replace the component. These kind of suggestions we are getting from the AI tools. So that much AI involvement in hardware designing and embedded product design lifecycle. So thank you. That's all for today. If you are having any doubts, please let me know. Mr. Sai Shankar is there for doubts clarification as well. So any doubts, dear faculty members? So let me hand over session to Surya. Surya, please. I will be on mute. Once Surya is interactive with you guys, I will open for doubts clarification. Surya, please go ahead.
Good evening, dear faculty. I think you have completed your session. So here is an announcement. As I previously informed you regarding our scholarship exam 2026, which is a part of our fourth year anniversary celebration and as a CSR activity. So we are very glad to announce that our national level scholarship exam 2026 has been launched, and registrations are open, and exam dates are 21st and 22nd February 2026. So registration starts from today and registration ends on 19th February, and it is exclusively for engineering students who is pursuing their first, second, and third year of ECE, and it's completely online AI proctored exam. Okay, so coming to exam domains, first one is industrial IoT and embedded systems, FPGA based VLSS design, and artificial intelligence and machine learning. So for this scholarship exam, we are giving 1.8 lakhs worth prize money across four domains, but first, second, third prize, as well as industrial internship opportunities. So we are very happy to launch this, and we are requesting you to take a part of this, requesting everyone to share the information which I am going to post in the WhatsApp group, and requesting you to share with your students, and if possible, yeah, sure. We'll share the PPT, and if possible, requesting you to give your share your CR numbers so that we can get in touch with them, and our team will get in touch with them, and they will share the details of scholarship exam. So that is all about the scholarship exam which we are going to conduct, and requesting everyone to share the information with your students, and requesting you to share your CR number if possible through our yeah through WhatsApp to make an effective communication between the students. So if you have any queries regarding scholarship exam, please let me know in the chat box, or else you can openly freely switch on your mic and ask your queries. Registration started. Nearly 500 plus registrations enrollments done till now. So we are requesting you to share the information with your students. And if possible, please share the CR contact with us so we'll get in touch with them.
Yeah, every year, as a part of every year, I'm the founder come CEO of Santami. So every year we are conducting multiple activities for student and skilling activities. One is faculty development program. Every semester we are conducting one FDP. At the same time, second thing is yearly once we are conducting scholarships for students. Last year, 1.2 lakh scholarship we provide for 10 plus students across India, and this time we make it as a 1.8 lakh of the scholarship amount. And one more thing, in every alternative centers we are going for a career catalyst talks, and one more thing, master classes on different industry trends, and VLSI, but our major focusing on semiconductors. Okay, so master classes will be there, and skilling programs is there, and career talks will be there, faculty development is there. So these kind of activities we are conducting every year. So if you are interested, you can collab with us somehow. Like we are the young entrepreneurs, we should want to educate as many as possible. That's what our main intention. So each and every time it's very difficult for you guys to share the info. It will be very helpful for the students if you able to pass the same information with the students. If you feel difficult, you can share your CR contact, or else you can add our team members in your group, so that only useful information will be shared, like not a spam kind of thing. Whatever the, like this particular CSR fund, every financial year there is a our company anniversary on Feb 23rd. So registrations will be start from today, and registrations will almost closed by 19th February, and exams will be on 21st and 22nd online. Majorly industrial IoT, embedded systems, VLSI, AML, these are the domains. So if interested, you can share the information with the needful students. Somehow it will be helpful for 12 students. So sorry, 16 students. So thank you guys. If you're having any doubts, please.
Thank you, Sudhir. So this is all about our scholarship exam. we are requesting everyone to share the information. We are going to share this information in the WhatsApp group. If possible, requesting you to please share your CR contact. We'll get in touch with them and we'll share the information related to scholarship exams, related to career catalyst talks, and related to master classes or other future activities which we are going to conduct. So we'll share with them. Thank you so much. Thank you, please.
Thank you. Thank you, respected faculty members.